Approximately 4.5 billion years ago, a transformative event occurred in the cosmic narrative as Earth experienced a cataclysmic collision with an ancient protoplanet named Theia, reminiscent of Mars in size. This momentous impact unleashed an intense shockwave, resulting in a colossal debris field that eventually coalesced to give birth to our celestial companion, the Moon. Referred to as the giant impact hypothesis or the Big Splash, this scenario posits that Theia struck Earth at a velocity of 9.8 km per second and an angle of 45 degrees, creating a shockwave that enveloped our planet over subsequent hours, leading to the formation of a debris field from which the Moon emerged over millions of years. However, recent research introduces a groundbreaking perspective, suggesting that the Moon might have rapidly materialized within a mere few hours, challenging the conventional understanding of its origin. The monumental Apollo 11 mission played a pivotal role in unraveling the mysteries of the Moon's formation by bringing back approximately 1.6 kilograms of lunar rock and dust. Analyzing these samples unveiled their ancient age, dating back around 4.5 billion years, signifying that the Moon took shape approximately 150 million years after the inception of our solar system. This era coincided with a tumultuous period marked by collisions with smaller planets, one of which potentially gave rise to the Moon. The celestial culprit behind this collision, Theia, is thought to have been comparable in size to Mars. The conventional hypothesis posits that Theia fragmented into millions of pieces upon colliding with Earth. These fragments subsequently merged with vaporized rocks and gas from Earth's mantle, forming a disk that gradually solidified into a molten sphere, eventually evolving into the Moon. However, recent research injects a compelling twist, proposing that the Moon might have rapidly taken shape within a span of a few hours. To scrutinize this alternative theory, researchers harnessed the power of a computer program called Swift, simulating numerous Earth-Theia collisions with varying angles, spins, and speeds. These simulations, conducted on the Cosmos supercomputer, intriguingly suggested that the Moon could indeed have formed swiftly from ejected Earth fragments and shattered Theia pieces within a condensed timeframe. This novel hypothesis provides a plausible explanation for some of the Moon's distinct characteristics, including its wide-tilted orbit, thin crust, and partially molten interior. Nevertheless, the validation of this theory hinges on acquiring additional evidence, particularly from the lunar mantle. NASA's forthcoming Artemis mission is poised to play a crucial role in this quest by extracting rock and dust samples from beneath the Moon's surface, offering invaluable insights into the Moon's evolution over billions of years and serving as a litmus test for the credibility of these simulation results. The intertwined histories of Earth and the Moon underscore the profound significance of unraveling the Moon's formation, serving as a beacon that illuminates our understanding of the intricate evolution of our home planet. In a concluding note, the 34th episode of the Sunday Discovery series encourages viewers to actively engage with the content by liking, subscribing, and enabling notifications to stay abreast of future episodes and continue the enlightening journey into the mysteries of our cosmos. The Moon does not possess a global magnetic field like Earth. However, certain regions on the lunar surface exhibit localized magnetic fields, likely remnants of past volcanic activity when the Moon had a more active molten core. The Moon's surface bears witness to a long history of impacts. Some of the largest impact basins, like the South Pole Aitken Basin, are remnants from ancient collisions that occurred billions of years ago. The bright, mountainous regions on the Moon are referred to as lunar highlands. These areas are older than the Dark Maria and are thought to be the original crust formed during the Moon's early history. A lunar eclipse occurs when the Earth passes between the Sun and the Moon, casting a shadow on the Moon's surface. During a total lunar eclipse, the Moon can take on a reddish hue, often referred to as a blood moon, due to the Earth's atmosphere scattering sunlight. The Moon provides a unique microgravity environment that researchers can use for experiments and studies. This environment, while not as strong as Earth's gravity, is still sufficient for various scientific investigations. The lack of a substantial atmosphere on the Moon means that its surface is exposed to cosmic rays from the Sun and beyond. Understanding these cosmic rays can provide insights into space weather and radiation exposure for future lunar missions. In addition to the Apollo missions, several robotic landers and rovers have explored the Moon. For example, China's Chang'e missions have provided valuable data and images, contributing to our understanding of the lunar surface. The moon has played a significant role in human culture, mythology, and literature throughout history. It has been a source of inspiration for art, poetry, and religious beliefs in various cultures around the world. Unusual bright swirls on the moon's surface, known as lunar swirls, are thought to be caused by the interaction of the moon's magnetic field with solar wind and micrometeoroid impacts. Their exact formation mechanism is still under investigation. Several countries and international collaborations are involved in lunar exploration and research. The moon has become a focal point for global space agencies, fostering international cooperation in space exploration. Some researchers have proposed the moon as a potential source of helium-3, a rare isotope that could be used in future fusion power technology. While this idea is speculative, it adds to the discussion of the moon's potential role in future energy solutions. There are plans to build a lunar gateway, a space station orbiting the moon, as part of international efforts to support sustainable lunar exploration. This gateway could serve as a staging point for future crewed missions to the lunar surface and beyond. These details provide a more comprehensive overview of the moon's scientific characteristics, historical significance, and ongoing exploration efforts. The moon formed through a process called the giant impact hypothesis, where a Mars-sized object collided with the early Earth, ejecting debris that eventually coalesced to form the moon. The moon has a layered structure, consisting of a thin crust, a solid mantle, and a small, partially molten core. It is composed mostly of rocks rich in aluminum and silicon, with some iron and magnesium. The moon's surface is characterized by impact craters of various sizes, caused by collisions with asteroids and comets. It also has flat, dark regions called lunar maria, which were formed by ancient volcanic activity. The moon's surface is covered by a layer of regolith, a fine layer of dust and rocky debris resulting from the constant bombardment by micrometeoroids over millions of years. The moon experiences extreme temperature variations. During the lunar day, temperatures can reach around 127 degrees Celsius, 260 degrees Fahrenheit, while during the night, temperatures can drop to about -173 degrees Celsius, -280 degrees Fahrenheit. Unlike Earth, the moon has a very tenuous and virtually non-existent atmosphere. It consists of trace amounts of gases, including helium, neon, and hydrogen. The moon's gravitational force is much weaker than Earth's, about 1/6 of Earth's gravity. This lower gravity makes it challenging for the moon to retain a significant atmosphere. The moon is tidally locked to Earth, meaning it always presents the same face to our planet. This is a result of gravitational forces over time and has led to a near-permanent near side and far side of the moon. Moonquakes, or seismic activities on the moon, were discovered during the Apollo missions. They are less frequent but can be more profound and last longer than earthquakes on Earth. The causes of these moonquakes are still not fully understood. Recent discoveries from lunar missions, such as the Lunar Reconnaissance Orbiter, suggest the presence of water ice in permanently shadowed craters at the moon's poles. This finding has implications for future lunar exploration and potential resource utilization. The moon's gravitational influence on Earth is responsible for the tides. The gravitational interaction between the Earth and the moon also contributes to the stabilization of Earth's axial tilt, which has significant implications for climate stability over long periods. Various space agencies and private companies have plans for future lunar exploration, with ambitions to establish lunar bases, conduct scientific research, and use the moon as a stepping stone for future human exploration of Mars and beyond.